Hello students, I welcome you in today's session of physics. And in physics, as you all know, we were discussing a topic, gravitation. Fine. This is your chapter number 11 of physics. We had almost covered in our previous 4 lectures most of the topics of gravitation. Now today we are going to discuss the gravitational field. Fine. So you can see here, this is the topic we are covering for the today's class. So every particle in the universe attracts every other particle with a force which is called gravitational force. I hope you know very well. So the space around the attracting particles in which the gravitational force of that particle can be experienced is called its gravitational field of that particle. Fine. Now here you can see that the gravitational field is strength. So the force experienced by a unit mass, clear, which is placed at a point in the gravitational field is called its gravitational field strength, or you can say it the intensity of gravitational field at that point. So this definition is on the assumption that the unit mass itself does not make any change in the original gravitational field. Means 1 kg mass if you suppose taken, then it will not create any effect over the gravitational field. Fine. So that is the thing written here. Now let us suppose if F force F Newton acts on a mass of m kg which is placed in the gravitational field, then the gravitational field strength will be how much? F upon m. Clear? Newton per kg, and its dimension you can see here LT minus 2. This is the dimension. The gravitational force acting on a mass small m which is placed at a point distance small r from a mass capital M is given by, you know very well this formula, we had already discussed in our 4 previous lectures. F is equals to G m m, where m is the mass of the earth and small m is the mass of other body and r is the distance between the two bodies. So the intensity of the gravitational field you can write this like this. You put the value of F in place of F upon m in this formula. So what you get here F upon m equals to Gm by r square. Clear? This is the intensity of gravitational field. Fine. And as you know very well, the gravitational field is a vector quantity. Clear? Now we will talk about what is gravitational potential. You have read about in the previous classes electric potential, fine, magnetic potential. So here we will talk about the gravitational potential. Suppose if a body take away from the gravitational field, so what you have to done, work is done against the gravitational of attraction, fine, experienced by the body. On the other hand, if we bring a body from outside into the gravitational field, then the field itself will work on the body. So you have to remember one thing here, I would like to clarify, when the work done is taken as positive and when the work done is taken as negative. So work done is taken as positive when you are doing work, fine, like you are moving against the gravitation force of attraction and you take a body upward direction and the gravity is attracting the body downward direction. So you are doing work over the body to move it away from the gravitational force, fine. Now when we take gravitation work done as negative, so work done is negative when the gravitation force already doing work over the body, you are not doing any work over the body. In that case the work done is always taken as negative, fine. So the work done in bringing a unit mass from infinity to a point in the gravitational field is called its gravitational potential at that point. This is the definition of gravitational potential. Clear? How can you define it? The work done in bringing the unit mass from infinity to a point in the gravitational field is called its gravitational potential at that point. This work is obtained, not done by the agents in bringing the mass. Clear? So as you can see here, if W with the work done obtained in bringing a body of mass m kg from infinity to a point in the gravitational field, then you can write the potential like V is equals to W by m, which is joule per kg. Clear? Since work is obtained, that is negative, and the gravitational potential is always taken as negative, fine, and it is a scalar quantity which has dimension of L2 minus 2. I hope it is clear. Now this is the vector relation of how can we vectorally prove the gravitational potential due to a point mass. So you can see here, suppose a point mass which is m is situated at a point O. Clear? Let A be a point in the gravitational field of mass m, distance is small r from O. You can see here this is the distance is small r, and here you have to find out the gravitational field potential. Fine. So for this, let a unit mass be placed at a point A, then the gravitational force acting on it due to m is how much? F is equals to g m by r square, and it acts towards O, and this force is acting towards this direction. Now let us suppose the unit mass moves against this force from A to B. You can see here we displace the unit mass from A to B through a small distance, which is how much? dr. Then the work done against the gravitation would be how much? As you know, here the displacement is very small, so the work done is also very small. So dw equals to f dr. By using the formula w equals to f into d, means work is equals to force into displacement. Fine. So from that formula we write this equation like this, clear? And if we integrate it over the limit r to infinite, so you will get the relation like g m by r, clear? So finally, after solving all the values, you can see here the work done, then the unit mass moved from infinity to A will be minus g m by r. This will be the gravitational potential V at a distance is small r from the mass m, that is V is equals to minus g m by r. I hope it is clear. Now what happened if we talk about the gravitational potential on the earth surface? So you can see here the same formula which we use in the above expression, F is equals to g m e by r e square, clear? It is on the surface of the earth, force of attraction. Now the work obtained in bringing the mass small m from infinity to the surface of the earth along the gravitational force is given by W equals to minus g m e m by r e, clear? So how can we write this formula? We put this value, or you can put the value of g m by r, gravitational potential on the earth surface, V is equals to W by m. So in place of V you can write this value which is equals to this, from this relation, minus g m by r e. I hope it is clear. Now there is a relation we had already set up, acceleration due to gravity and the universal gravitation constant. In our previous lecture I taught you about this. So g is equals to g m e by r e square. So you can write this formula like g m e is equals to g r e square, clear? So from this relation, if we put the value of g m e in this equation, the potential comes out to be like this, minus times of g r e, or you can also write this V is equals to minus g r e. If we talk about the height above the earth's surface, then in that case the gravitation potential changes to like in this form, clear? Fine. Now we will move to the gravitational potential energy. You can see here this thing we are going to discuss right now, gravitational potential energy. So the work obtained in bringing a body from infinity to a point in the gravitational field is called its gravitational potential energy. Fine, this is the definition. I hope you know very well what is potential energy. The energy which is stored in a body due to its position is called its potential energy. So the gravitational potential energy at infinity is assumed to be 0. Fine. Because why it considered it 0? Because work is obtained not done in bringing the body from infinity into the gravitational field. So the gravitational potential energy is always taken as negative. Now you can see here, suppose if a particle of mass is small m, which is at a distance is small r from a gravitational mass capital M, so that its potential energy will be how much? U is equals to work done from infinity to r, where work done from infinity to r is the work done by the gravitational force on the particle as it moves from infinity to a distance is small r. Fine. Now let us suppose if capital F with the gravitational force acting on the particle when it is at a distance small r from the gravitational mass, then we can write this expression like this, U equals to W infinite tending to r, or you can also write in place of W F dr. You know very well work done equals to force into displacement. So when you solve it, you will finally get the expression potential energy is equals to how much? Minus g m by r, clear? So this is the potential energy. Now the same thing here you can see the proof for the potential energy of a body on the earth's surface. So you can see here, this is the figure, this one. What they did here? Let m e be the mass and r e be the radius of the earth. Suppose a body of mass is small m is placed at point B at a height is small x from the center O of the earth. You can see here, this is figure number 12. So then the gravitational force of attraction, you know very well, the gravitational force of attraction is equals to how much? F is equals to g m e m by x square. So the work done in taking the body through infinitesimally small distance dx, you can see here from C to B or B to C is equals to how much? dw equals to f dx, that is g m e m by x square or dx. So the work done in taking the body from infinity to the point A on the gravitational field, it comes out to be, after solving the whole expression from the limit x to Re, fine, minus g MEm by Re. So you can see here the work obtained in bringing the body from infinity to the earth or at a height h from the earth's surface, that is the gravitational potential energy of the body on the earth's surface, is equals to how much? U is equals to W, or in place of W you can write here g MEm by Re, fine. And as you know very well, there is a relation between the acceleration due to gravity and the gravitational constant, this one. So from this relation we can also write it like g Me equals to g Re square. So what happened? The potential energy at the surface of the earth changes to this form, minus g Re into M. So if the body is above the earth's surface at a distance small r from the center of the earth or at a height small h from the earth's surface, then its potential energy comes out to be how much? U is equals to minus g Me by R, or if you consider it above the earth's surface, in that case the radius is added up with the height, clear? Or you can also write it, this potential energy, in terms of the acceleration due to gravity. I hope it is clear. Now further, in the above equation, m, if we consider the mass equals to 1 kg, so in that case the potential energy is equals to the potential of the body. And what happens if the distance is very large as compared to the radius of the earth? So the potential comes out to be like this form, V is equals to minus Gm by Re, or you can also write it minus Gm by Re plus H, where Re plus H is the above the surface of the earth, fine. And this relation is with respect to the acceleration due to gravity. I hope you understand it. Now we will talk about the maximum height attained by the projectile. So you can see here, you had read about the projectile motion in the previous chapters. So you can see, we will talk about now the maximum height attained by the projectile. So on the basis of gravitational potential energy, we can determine the maximum height attained by a body projected upward with a certain velocity, or the velocity of projection required by the body to reach a certain height. So what happened? M be the mass of the projected body. If the mass of the earth is Me and the radius is Re, then what happened? The gravitational potential energy of the body on the earth's surface comes out to be U is equals to minus g MEm by Re, clear? The gravitational potential energy of the body at a height small h from the earth's surface would be like this. So increase in the gravitational potential energy, this is above the height, you subtracted the gravitational potential energy at certain height minus at the surface of the earth from this equation. So after solving out all the expression, you can see here, this is the final expression you will get. Now suppose the body is thrown upward with a velocity of how much? V. What happened? As the body goes up, the kinetic energy, you know very well, the formula of kinetic energy is half mv square, given to it's continuously converted into potential energy, because at a certain height reaching its velocity goes on decreasing, fine. So the body goes up to that height where it is a whole initial kinetic energy is converted into its potential energy, fine. So after this it will start falling downward. Therefore if the maximum height attained by the body is h, then what happened? Its kinetic energy is equals to how much? As you know where it is written here, the whole of the kinetic energy changes into the potential energy. So V equal this potential energy equals to the kinetic energy, and after solving all the things you will get here V square is equals to 2dh 1 plus h by Re. So the maximum height attained h by the projectile, from this relation you can also find out the maximum height attained by the projectile is equals to this one. How much? H is equals to V square Re by 2g Re minus V square, fine. Now suppose we want to send a body to a height h is equals to Re, means which is equals to the radius of the earth. Then what happened? Put the value here and you will get this relations, fine. So after solving and putting all the values, you know very well there is a relation between escape velocity, relation between V is equals to under root g Re. So in place of g and Re, if you know the acceleration due to gravity and radius of the earth, so you can find out the velocity through which you can throw a body, fine. So this is 7.9 km per second. I hope this is clear. Now we will talk about what is escape energy and escape velocity. Here you can see that this is the topic 11. What happens if we project a body upward, then after reaching a certain height, the body returns due to the gravitational attraction of earth. So if we go on increasing the initial velocity of the body, then it returns after reaching greater and greater height. Fine. So ultimately, at a certain velocity of projection, the body will go out the gravitational field of the earth and will never return to the earth. So this initial velocity of the body is called this escape velocity. So what is escape velocity? The velocity through which you project a body upward direction and it will not come back to the gravitational field. This is called its escape velocity. And the energy, or you can say the kinetic energy given to a body to project it with escape velocity is called its escape energy. We have read that assuming gravitational potential energy 0 at point infinity, so the gravitational potential energy of the body of mass is small m placed on the earth's surface is equals to u minus gme m by re, where me is the mass and re is the radius of the earth. So in order to take the body from the earth's surface to infinity, the work required is how much? Gme by re. Clear? Now it is evident that if we throw a body of mass m with such a velocity that its kinetic energy is gm by re, then it will go in space outside the gravitational field of the earth. So you can write this expression like this form: escape energy is equals to plus of gme m by re. I hope you understand it. The velocity given to a body is the escape velocity. Clear? Let it be v, then the kinetic energy of the body comes out to be half mve square. So you can see here, this is the kinetic energy, and we compare both the equations. Gme m by re equals to half mve square. So after solving all the expression, you will finally get here the escape velocity equals to how much? Root 2 gme by re. Thus we see that the escape velocity is independent of the mass of the body. This is the important one. So if g with the acceleration due to gravity of the earth, then you can write here this relation g is equals to gme by re square. You know this relation very well. Now substituting, or you can also write it gme is equals to gre square. Now we put the value of gme in place in this equation, the above one here. Fine. In this equation, in this equation number 1, what we get here, ve is equals to under root 2 gre. So we can use equation 1 and 2 calculate the escape velocity further. So acceleration due to gravity comes out to be 9.8 and the radius of the earth is this. After putting all those values, you will get the escape velocity how much? 11.2 kilometers per second. Means if you project a body above the earth's surface, then it will go out into space. Clear? So that is the thing is written here. Now you can see here there are few discussions they are taking here, number 1, number 2, number 3, number 4. So first we discuss about number 1. So as the escape velocity is independent of the mass, you can see from the above formula of the body and its angle of projection from the surface of the earth or planet. Now the second one, the value of escape velocity depend upon the mass and the radius of the earth planet from the surface of which the body is to be projected. So the escape velocity will be different for different planets. Talk about the third one. If a body is projected from the earth planet with a velocity v such that the v is very less than escape velocity, then after reaching a certain height, either the body will move in the orbit around the earth planet or it will fall back to the planet. Now come to the fourth one. If the velocity of projection of the body, which is the small v, from the surface of the planet is greater than the escape velocity v of that planet, then the body will escape out the gravitational field of the planet and it will move in the interstellar space with a speed of v dash. So we can obtain using law of conservation of energy. I hope you are familiar with the law of conservation of energy. You can see here, this is the law of conservation of energy written here. This one, total energy of the body at earth planet equals to total energy of the body at infinite. So all these, after putting the value, you can see here half mv square plus minus gmem by re in interstellar infinite energy. This you will get the relation v dash is equals to v square root minus ve square, this one. Now this is the important one. What is the relation between orbital velocity and escape velocity? So the orbital velocity of a satellite close to the earth is, and the escape velocity for a body thrown from the earth's surface is ve root 2 gre. You know this expression very well. So if we divide this orbital velocity with the escape velocity, you can see here root gre by under root 2 gre, you will find out that ve is equals to root 2 times of v naught or v orbital velocity. So if the orbital velocity of the satellite revolving close to the earth happened to increase root 2 times, the satellite would escape. So that's the end of the today's class, student. The remaining topics of consequences of escape velocity we will discuss in our next lecture. Thank you class. Thank you very much.